Welcome to today's lecture. Today we want to look at infinite sequences. Infinite sequences. So I will start with an introduction, and then I will state a couple of theorems that we need to understand what sequences are, and also understand the convergence of sequences. So a big part of this lecture has to do with, if you have a sequence, how can you determine if the sequence is convergent or is divergent? That is the principal thing that we want to look at today. So a sequence basically is a list of numbers, if you like, a1, a2, a3, and so on, an to infinity. Okay, so sometimes you can represent them by curly brackets like this. Other times you can do things like an and give the indices, say from 1 to infinity. It doesn't have to be starting from 1, it can start from any number. So basically that's how you represent this set of infinite sequences. Okay? So for example, there are cases where your nth term of the sequence can be given by, let's say, 2n all over n plus 1. And so you can list all the different numbers within this sequence, right, by putting in different values for n, so that the list becomes, if n is 1, for instance, you're going to have 2 over 3. If n is 2, you have 4 over, this is 2, 4 over 3. Okay, this is the case when n is equal to 1. And when n is equal to 2, you get that. When n is 3, you're going to have 6 over 4, and so on to infinity. So these ones will give you the different terms of this given sequence. Okay. Sometimes, well, you don't have a single expression like this giving you the terms of the series, of the sequence. For instance, the Fibonacci sequence, for instance, you have sequence is given by, you have the first term, which is 1, you have the second term, which is also 1, and then for subsequent terms, you're going to have f of n, which is f of n minus 1 plus f of n minus 2. This is the case when n is greater than or equal to 3. And so you can list the times of this sequence as this 1 and 1. When n is 3, you add this and that gives you 2. This plus that gives you 3, this gives you 5, 8, 13, and so on. Okay, so these are just simple examples of what sequences are. There are times you have an expression, nice, simple expression that you can use to give you the terms of the sequence. Other times you have a recurrence relation, like the Fibonacci sequence. Okay? Good. Now, an important point about sequences is you want to know whether this sequence is converging, approaching a certain number, okay? And that is called the limit of the sequence. And so let's talk a bit about that. And so if you look at a sequence I just wrote down, where an was equal to 2n plus say n plus 1. You can actually show that if you plot this on a graph, this is n, and these are your an's. Okay, you have points that will start from somewhere here, there, and there, and there, and you can actually show that this sequence is approaching the number 2. Very soon we'll see how that is the case. Okay, now. So, if the terms of the sequence as n goes to infinity is approaching a certain number, then we'll say that number is the limit of the sequences. So in this case, we'll say that the limit as n goes to infinity of your an is equal to some number, let's call it L. Okay? What this means is that I can let the terms of the sequence, the an's, approach this L, this number L, by taking n large enough, sufficiently large. If it's a big number, I can always make these terms approach that. Okay? So, if you like, that is an intuitive way of describing what the sequence, the limit of the sequence is. There is a more precise mathematical definition of that, which says that if I have for every epsilon greater than 0, right, the limit as n goes to infinity of AL is L, means that I can always choose some n such that this guy is always less than epsilon for some n greater than big N. Okay, mathematically. So this says that if this is my L, if this is L, I have a sequence that is approaching L. It says that I can, for every epsilon, I can always choose this, no matter how small it is. I can find an n such that this sequence will always lie within this band, right? Where this is L minus epsilon plus epsilon, L minus epsilon. So that after whatever, let's say this is n is equal to big N. Okay? For every epsilon, no matter how small, I can always find an n, some big N, such that the terms of the sequence will always lie in a band like this, always approaching this. If that happens, we say this number L is the limit of that sequence. Okay. So it's important to understand this concept of the limit of the sequence because we'll come back to that later on. All right, so here are a few theorems, what I call some useful theorems. To note about sequences. I'll write a couple of them down, and then we'll use them to explain sequences, the convergence of sequences. So here it says that here if theorem number 1, so let's call it theorem 1. Okay, this is one of the important ones. If the limit as x goes to infinity of f of x is equal to L and f of n is equal to a n when n is an integer, then the limit as n goes to infinity of a n is also equal to L. So this is the first theorem that we'll work with, and this is going to help us to find the limit of a sequence. In other words, which numbers does the sequence converge to? So let's use an example to illustrate this. Okay. So for instance, we want to find the limit as n goes to infinity of say 1 over n to some power r, where r is greater than 0. Okay, how do you find this? So to find this limit, we can rewrite this using a related expression in terms of x, where x is a real number. Okay, so we can rewrite and find, in place of n, we're going to use x and find the limit as x goes to infinity over 1 over, this is x raised to the power r. Now, r is positive, x is a real number. Okay, since this is positive, for instance, 2 or 3, 1 over x squared, for instance, what do you get? Find the limit as x goes to infinity. From calculus 1, you know this is equal to 0. Because the x here is r. This theorem says that if I can rewrite this in a related expression using x, then I can conclude straight away that because this is true, the limit as n goes to infinity, where n now is an integer of 1 over n raised to the power, is also equal to 0. Okay, so that is a direct application of this theorem. So that's theorem number 1. Theorem number 2. Well, before we do that, we'll write down a few laws of sequences that we'll be using along the way. Okay. So we have limit. Get rid of this. Limit. Laws for sequences. Okay. So I'll just write a few of them. That the limit as n goes to infinity of an plus. Well, this is important. Here, if this sequence an and the sequence bn are convergent, okay, they converge to some number, then these hold. Number 1, the limit as n goes to infinity of an plus or minus bn is equal to the limit as n goes to infinity of an or plus or minus limit n goes to infinity of bn. I'll rewrite like this. If these limits are convergent, right? They are approaching number. Another important one is if I have limits as n goes to infinity of, let's see, with some constants of an, then of course I can just pull c out of the limits and find the limit as n goes to infinity of an. Okay, let's write down one more important one. This is the limit as n goes to infinity of, let's say, of an raised to the power p, where p is greater than 0, of course, n is an integer. If this is the case, I can do this. I can find the limit as n goes to infinity of an and raise all of this to the power p. Okay? So these are some limit laws that are important, and I will be using this along the way, okay, as we try to prove and use some of the theorems that will be stated. Now, let's move to theorem number 2 that we need. Theorem is called the squeeze want to look at the squeeze theorem. Okay, it says that, so number 2 says that if I have a sequence bn that is squeezed between two sequences Cn for n greater or equal to some n, and the limit as n goes to infinity of an is equal to L, that is the limit n goes to infinity of Cn, then the limit as n goes to infinity of bn is equal to L as well. Okay? So this is the explanation for this theorem. So the squeeze theorem basically says that if I have, similar to the squeeze theorem that you saw in calculus 1, if I have a sequence, let's say this is L and N, I have a sequence that is, let's say, approaching L. I have another sequence, so let's call this one Cn, and I have another sequence, let's say this, it's also approaching L. Let's call this sequence An. And there is a third one, okay, that is in between these two. The value of Bn is always, for each n, lies between that of An and Cn. And let that be whatever you want to use symbols for. Let's say it's something like this. This is the sequence. This is the sequence. This is another value is another point. Okay, so the squeeze theorem says that if these sequences, these guys here, always lie between these two, and Cn and Bn are approaching the number L, then the sequence Bn, these guys, this must approach this as well, because it's squeezed between the two. Basically, that is what it says. Okay, so let's use an example to illustrate how you use the squeeze theorem, okay, to solve some problems. So here, this says we want to find the limit as n goes to infinity of n factorial all over n raised to the power n. Okay? Okay, this is n factorial all over n raised to the power n. Okay, so let's see how you do this. So sometimes it's helpful to write down the first few terms of the sequence. It helps you to see the behavior of the sequence. So we're going to let a and b equal to n factorial all over n raised to the power n. When n is 1, I'm going to have a1, which is 1 factorial over 1. 1 to the 1 is 1, so this is just 1. A2 will be 2 factorial all over 2 to the power 2. So this is basically 2 over 4. If you like, 2 times 1 over 4, which is 2 times 1, 2 times 2. So if you like, A1 is 1, A2 is basically, these guys cancel, it's basically 1 over 2. Let's see what A3 looks like. A3 will be 3 factorial all over 3 raised to the power 3. This is the same as 3 times 2 times 1 all over 3 raised to the 3 is 3 times 3 times 3. Okay. So we can go on and on. And of course, the an1 will be n factorial, which will be, of course, now I can rewrite it this way. I can write this as 1 times 2 times 3 times n. Okay. N to the n will be n times n times n. N factors, n of them. So I get this. Let's come this way. Okay, so which means I can rewrite my an to be equal to 1 over n multiplied by, I have 2 multiplied by 3, this times n, this is n, n. Alright? Now this is important here, so pay attention here. Here, what is in parentheses can actually show that this quantity here cannot be greater than 1. Okay? This is what it shows. So note that 2 times 3 times n times n. This guy has to be less than or equal to 1. I mean, it can only be equal to 1 if each of these, right, terms before n are 1. I mean, they are n's. If these are n's, then this cancels this and you have 1. But if n is greater than these numbers, then of course it has to be less than 1. Alright? Something smaller on top, something bigger at the bottom. So this holds. Now I can multiply both sides by 1 over n, and it's positive. So this implies that 1 over n multiplied by 2 times 3 n times n times n has to be less than multiply this by 1 over n, and I get this. Okay? But this guy here is of course a n. So this implies that a n has to be less than or equal to 1 over n. Okay? But also note that the terms, okay, from this, you see that the terms of the sequence are always positive. Okay? Each time of this and they are never negative, which implies that this a n here must always be greater than 0, and this is less than or equal to 1 over n. Now from here, I can take the limit of each term, okay, of this inequality. So as n goes to infinity, this is what I'm going to get. So as n goes to infinity, this remains at 0. This is less than the limit. N goes to infinity of an less than the limit. N goes to infinity of 1 over n. Okay, so we just showed that if I have 1 over n to the power r, and r is positive, this goes to 0. So straight away we know this also goes to 0. So this implies that 0 less than the limit, infinity, and this has to be less than or equal to 0. Okay, so because I have 0 on the left hand side, 0 on the right hand side, the squeeze theorem says that this has to go to 0. So by squeeze theorem, I have limit as n goes to infinity of n. This must go to 0. Okay, so that is an example of how you use the squeeze theorem.